My jokes are better than Aaron's. I could tell a bunch of jokes about grad students, but I think that's not allowed. Now, he did a good job. I watched the lecture. Let's give him a round of applause, because we'll probably watch this one. So, he's going to be back on Tuesday. Finish this out. This is where we're going to pick up, because I want to make sure that you guys know the difference between local potentials and what we're going to talk about in more detail, action potentials. So one can cause the other. Which one causes which? Which causes which? Local causes action. We're getting into the real tough material for the semester. So I'm still doing some makeup exams. So the exams won't be passed back yet. Those test scores are posted, so you can see those. Historically, this next exam is one of the lower averages. Yes, yes. Someone's excited about that competition. So this, or you're just confirming, you're agreeing with me. Oh, I see, okay. That wasn't enthusiasm, that was agreement. Check. So this exam tends to be one of the more difficult ones, apparently. So I think it would behoove you to come to SI sessions, to come to the peer TA session this afternoon from 4 to 5, and make sure you have a firm grasp of this material. If you don't, ask questions early, like this week. Don't wait till next week. So a local potential can cause an action potential. These local potentials have other names. Another name for them is a graded potential. So a graded potential is just another name for an action potential. Two words referring to the same thing. Graded/local. And these two terms get their names from some of the features or characteristics of these types of potentials. It's a local potential, meaning that it only exists in a local area and it's not transmitted or propagated downstream. Or it's considered a graded potential because it has a level to it, or a grade. It doesn't reach threshold. So because it has a level or a grade to it, and it doesn't reach threshold, it doesn't propagate the signal downstream, which would be considered what? An action potential. So there's definitely a difference between a local potential, otherwise known as a graded potential, and an action potential. You will need to know the difference between the two on the exam. You'll have to compare and contrast them. A local potential could be a depolarizing event, meaning that it makes the cell less negative and brings it closer to zero. Or it could be a hyperpolarizing event, where it actually makes the cell more negative, gets it further away from zero, and that would be an excitatory state or an inhibitory state. In an excitatory state or an inhibitory state, if you made it less or more negative meaning minus 90, minus 100, it's inhibited. So another name or subcategory of graded or local potentials are called inhibitory or excitatory postsynaptic potentials. And we abbreviate them EPSPs or IPSPs. And we'll talk more about that in the subsequent lectures, but I want you to understand that IPSPs or EPSPs, I is for inhibitory, so that's a local potential that hyperpolarizes the cell, that makes it more negative. A EPSP, or an excitatory postsynaptic potential, is one that depolarizes it or makes it less negative, approaching threshold. Once it adds up, or summates, to threshold, then you fire the action potential. So here you can see some examples of how you would summate or add. So here's a deflection that's in the positive direction, so that's a depolarization event, that's excitatory. Here's a counterpart in the negative direction that would be inhibitory. So that's how they would look. Here's a timing of an event. This one's actually a larger magnitude than this first one. And so you can see that the potential is bigger in size. Here you can see that are two really close to each other, and they fire, and the second one fires before the first one can dissipate or fade away, and so it adds up and makes this larger than this first one. So you can stack these excitatory postsynaptic potentials essentially on top of each other. Now the characteristics of these, that they're graded, meaning their magnitude is going to depend on the strength of the stimulus. They can be regulated by ligands. They have a certain number of initiators that cause them to take place. Things like energy, like heat, or light, or force, mechanical. Neurotransmitters can stimulate a local potential. We'll have examples of all of these in the next couple of lectures. But this is kind of foundational, so I just want to make sure from Tuesday, this is from Tuesday's lecture, you kind of walk away with these. Some characteristics of local is they go away fast. They dissipate rapidly. Another word for that is they're decremental. So if they're not used, then they fade away, and if you don't send a second signal fast enough, then you won't get this summation event. They're reversible in this manner. If it's not reaching threshold, then it doesn't fire the signal downstream. In contrast, I know you've looked into action potentials. Is an action potential reversible? No. If you listen to this question carefully, in contrast, I already gave you the answer, right? By the way, I asked the question. In contrast, an action potential is not reversible. Once you fire it, you can't change your mind. You cannot bring it back. It propagates downstream. But these guys don't necessarily reach threshold if they're not summated at threshold, so they can be considered reversible. And then we already kind of covered the hyperpolarizing or the depolarizing. Okay? Questions? There's a couple of review questions that you didn't get to, so let's talk about them real quick. Which of the following is not part of the central nervous system? A, nuclei. B, oligodendrocyte. C, microglia. D, Schwann cell. E, ependymal cell. Two of the above or all of them are part of the CNS. The Schwann cell is what? Part of the PNS, the peripheral nervous system. Okay, how about this one? Sodium potassium pumps in neurons consume an estimated 20% of all the energy in your body. Why? A, they're required to establish the resting membrane potential. B, they're required to maintain the resting membrane potential. C, they require 2 ATP molecules for each round of work. 1 ATP to push 3 sodium out, 1 ATP to pull 3 potassium in. D, I have no idea, but I know why I get tired. Yes, you get very tired when you study, and that's why you need to eat healthy. Mama says breakfast is the most important meal of the day. She's right. B, they maintain it. What establishes it? What establishes resting membrane potential? What is resting membrane potential? As a review from Tuesday. Minus 70. Or minus 70 millivolts. Thank you. Use the units. That was the most accurate way to say it. So what makes the cell slightly negative on the inside? Now, millivolts. So this is electricity, right? This is not any different than electricity that you and I utilize all day long. But we use voltage. These are millivolts. These are little volts. Okay? But you can disrupt the electrical conductivity of neurons with too much electricity, right? You've seen the cartoons. Okay? It's real. Okay? Or you can test it by putting your finger in the socket. That's not millivolts. Those are voltage. It'll give you a better zap. So what establishes the cell being negative on the inside? What's that? The charge of proteins inside the cell, which are anions, okay? And mRNA and DNA has a negative charge on it. And those are big items that don't leave the cell. So you already have kind of a slightly negative environment inside the cell, and the sodium-potassium ATPase pump just helps to keep that negative minus 70 millivolt steady, okay, in equilibrium. Okay. So that was Tuesday's lecture. And now we need to talk about today. So this is lecture 2 with action potentials. This is a nerd slide because you know you're a nerd when you see neurons in trees. Okay. So this is last season, and I was really excited when I woke up this morning. Did you guys see the mountain?
Yeah.
That's kind of wound up about it. Season passes, the preseason sales end on the 15th. So you guys get like the best deal, right? Because you're students, you get like the student rate. You should take advantage of that. Those of you that came in and you haven't been up there yet, shame on you. You should go up there. There's neurons everywhere. You can call mom and dad and tell them you're studying on the chair because you're looking at dendrites. Look at those look like dendrites. Okay. So I want you to draw a typical cell. This activity is what I want you to do right now. Typical somatic cell means a body cell. Really any cell in the body that has a nucleus. So draw one. And then after you draw it, somebody like, I'm not a really good drawer. Draw a circle, okay? It's not that complicated. Just like a round structure. Okay, it doesn't even have to be a perfect circle because most cells aren't. Your cell, your happy little cell, can be anything, any shape you really want it to be. And then I want you to, at resting membrane potential, that's what RMP stands for, I want you to show me where potassium, sodium, and chloride are in the highest versus lowest concentration. So you could just represent this. I don't need the numbers. Try to do it without looking at anything. Just see how well you're retaining information. Like a little self-test. If you have no idea, do you need me to explain where you're at as far as studying needs? Okay. So I use this as a self-test. I mean, you should be able to do this by now. If you can't, that means you're not spending enough time with this material. That's the new politically correct way of referring to studying. Right? Seriously, we read all this pedagogical research, and it's like, how do we get students to spend more time with the material? Like, isn't that like more words than necessary for the same meaning of studying? Yes, it is. Okay, but that's not the way that we write the papers anymore. So if you don't know where to start, you could draw a big NA and then a little NA, and the big NA is saying high concentration, the little NA is saying low concentration. Do the same thing with potassium, which is K. And you can do the same thing with chloride ion, which is Cl. How many think they're pretty confident they got it? Raise your hand, be proud. That's the extent of the confidence? Seriously. How many of you got it, but probably could brush up on it? Okay, that's honesty. That's fine. You are being video recorded right now. I'm just kidding. It's just recording up here. It doesn't record you guys. I'd have to get 4 releases for 300 of you. That would be a pain in the neck. How many of you, we're going to be looking at this over the next day or two, Dr. Keller? Nobody? There was like 25 hands that went up. Okay, so some of you aren't voting. All right, I saw 2 hands. All right, so it doesn't have to look this nice. Okay, but this is outside the cell, extracellular fluid. Inside the cell, intracellular fluid. You could draw this with a circle. That's inside the cell in the circle. Outside the cell would be the extracellular fluid, the ECF. You could get some colored pencils. I would honestly practice this activity because understanding where these ions are and their relative concentrations to each other will help you figure out what's happening. It's a really simple exercise to orient yourself. So the orange spheres are representing sodium. You can see sodium is in high concentration outside the cell, 145 milliequivalent, versus inside the cell it's at 12. You can see that there's more orange dots than orange dots in here. Potassium is colored in blue. You can see that potassium is higher inside the cell, so it would be a larger K plus inside the cell, and a smaller K plus outside the cell. And you can see that 150 milliequivalents inside the cell versus 4. Chloride ion, where is it highest? It's highest outside the cell. And the way that you remember that is the chloride ion likes to associate with the sodium under resting conditions and make essentially what? Sodium chloride, salt water, right? Our cells are basically bathed in a saline solution, a salty solution. So if you remember where sodium is high, you know where chloride ion is high. Does that make sense? As sodium attracts chloride. So, yeah. So 5.5 inside versus 110 outside. Do you need to memorize the numbers? No, I won't test you on the numbers. Okay? They're pretty simple, right? I mean, one's like, well, two of them are about at 150 milliequivalents, and the other one's at about 110 millimolar per liter. And then, you know, the small numbers are like 412 and 5.5. I mean, how hard is that to remember? But the reason it's important is, if I opened a sodium channel, which direction would sodium go? Why? Because of the concentration gradient. Agreed. Explain more. High concentration outside, low inside. I'm just repeating what he's saying up front. You flow from high to low, and we call that process what? Passive transport. There's another name for it as well. It's diffusion. No, facilitated diffusion is not this. This is passive transport diffusion. That was unit 1. Okay? Look out. You just remembered something cumulative. Okay? But see, here's the thing, guys, is you can't, this stuff has to be cumulative because you can't forget the concepts that we've already covered. Because they're relevant to the topics that we can keep going on. So if I open, I'm going to repeat that again because there's a lot of mechanism there. If I open a sodium channel, which way does it go? In. Why? It goes down its concentration gradient. We call that active transport or passive? Passive. Does it require ATP? No. Very good. Another name for it would be what? Diffusion. Very good. Could I write a test question A, B, C, D, E off of those answer options? Yes. Okay. So that would be a good thing to study. Yes, I probably will. If I open if I open a potassium channel, next, which way is potassium going to go? Why? It flows down its concentration gradient. Some people are like, I don't get the down. It's like it's going up on the slide. That true. No, I'm trying to anticipate what some of you might be asking. You may not say it, but you might be thinking it. It's going from high, which is inside the cell, to low, which is outside the cell. If I flip the slide upside down, it would still be going down its concentration gradient from inside the cell to outside the cell. You guys with me? Okay. So if I open this first, sodium comes in. If I open this next, potassium goes out. Everybody's comfortable with that? What's going to return to resting membrane potential? High sodium here and high potassium inside. because I've just moved ions. Now, how am I going to get them back to normal, homeostasis? Active transport, more specifically. Sodium's going to go out of the cell, I agree. Active transport, I totally agree. And there's a very specific structure that does sodium, potassium, ATPase pump. And it takes how many sodiums out? 3. And it takes how many? 2. Sodium's out 3, potassium's 2 in. 3 go out, only 2 come in. They're both positively charged, right? So that's a net loss of how many? 3 minus 2 is 1. I know, it's like really complicated. Do I need to write it down? 3 minus 2 is 1. Okay, 1 net loss, and the net loss is where? Inside the cell, because more positives went out, so now you have a slight negative charge, again, back inside the cell. Do you follow all that? Yeah. Okay, cool. All right. So now, with your drawing, if you didn't draw it now, copy this. I want you to divide up person A, person B. Give me some other examples. I just gave you 2. But give me some other examples. Person A, talk about voltage gates and ligand gates. Person B, talk about mechanical gates. Because I talked about what? I just talked about channels. I opened a channel. Yeah, you can go ahead and do that now.
I don't remember which ones. I don't know. Last lecture, wasn't it? This is we went through it at that point. Oh, okay, so ligand is something you connect with it in order for it to open. I would probably see right there, it says ligand is open, and that's when it will open. Yeah, it has to pair with something. And then it'll open and it'll let in the sodium. Yeah. It's just that. Foundation axon. Synaptic law. This is ACH.
Okay. So let me hear from some A people. Give me another example of a voltage gate. Any ideas? Give me an example of a voltage gate. Even if we already talked about it. What's that? Did you say no. Ion voltage gates, I agree. More specifically, what's an ion that we just talked about? Sodium. Okay? The nodes of Ranvier are actually where they're located. That's where they're physically located. So we'll get there. That was good. There's another one, calcium. Calcium voltage gates. Calcium voltage gates are really important for muscle contraction. And excitation, contraction, coupling. We'll get there. So sodium and calcium are 2 ions that respond to electricity that opens the gate. Okay? Any of you ever been to a gated community or live in a gated community? Right? And you pull up and you push the button and the gate goes open. That's not like some little gate troll that's opening the door. Right? It's usually like electricity is wired to it and then the gate opens. This isn't any different. Okay? It's not like hocus pocus. So the electricity triggers this gate to open, like that gate we just talked about, and then sodium is the only kind of object that can go through. Calcium does the same thing. Ligand gates. Anybody have an example of a ligand gate? What's that? Acetylcholine. So acetylcholine is a neurotransmitter. We'll get there. But I'm seeing how many of you have read head. I'm kind of pre-assessing you. Right? I'm your shrink. So acetylcholine is a neurotransmitter that binds to a receptor, and it opens the gate. So here would be another example. Right? You walk up to the gate, and you actually have to put a key in and turn it, and then it opens. That's your ligand that goes into its receptor. All right. Some channels. Give me some examples of some channels. What's that? The sodium potassium is really more of a transporter, so it's a pump. It has a channel, I would agree. Yeah, so I would take that one.
What about a protein channel?
A protein channel. So a channel is made out of a protein. It allows for certain objects to pass through it. And the one that you should be intimately familiar with is the potassium leak channel. The potassium leak channel is always leaking potassium out of the cell. Right? It's not regulated. It doesn't have a gate. It's kind of like, there's a hole in the boat, and it just slowly brings water in. But you have a bilge pump, so you can pump it out. Mechanical gates. What are these? So they're going to respond to force or pressure. And then the distortion of that membrane surface will cause the channel to open. So sensory receptors are really important for this, like for touch or pressure or vibration. Okay, let's try this particular question. What causes a cell to be negative? Causes. Another word would be what establishes it from the beginning to be negative. A, presence of chloride ion inside the cell. B, presence of chloride ions outside the cell. Oh, sorry. There we go. A, presence of chloride ion inside the cell. Presence of chloride ion outside the cell. Presence of nucleic acids inside the cell. Presence of proteins inside the cell. Or two of the above. Which two? C and D. Very good. So you didn't get confused by that. How about this one? This is where I was, huh? Which is higher in concentration inside of a typical somatic cell. Somatic cell just means any body cell. B. Potassium. Very good. Yeah. Okay. Let's watch this video with this in mind.
Unstimulated, neurons maintain a constant electrical difference or potential across their cell membranes. This potential, called resting potential, is always negative inside the cell and ranges from negative 40 to negative 90 millivolts. If a neuron is stimulated, the negative potential inside the neuron can be made either more or less negative depending on the stimulus. If potential is made sufficiently less negative, it reaches a level called threshold, and an action potential is triggered. During the action potential, the neuron suddenly becomes 20 to 50 millivolts positive inside. Action potentials last a few milliseconds before the cell restores its negative resting potential.
Okay. So that animation helps to kind of, I think, visualize what we're talking about when we're saying we're summating information and we propagate it downstream. And what you're propagating is, if you throw a stone into a calm pond, you can watch that ripple cross all the way to the other side. Okay? So if it's minus 70 inside, and you allow sodium ions to come in, you make it slightly positive, that is going to trigger the next adjacent area inside the cell to propagate that wave. Now, what's going to keep it from, why does it go forward? Why wouldn't it ripple with the stone? It ripples in all directions, right? But in a neuron, it only goes forward. It doesn't go backwards. Bless you.
Because it's hyper, like it's trying to do a hyperactive response, it can't go back.
Yeah, it has a hyperpolarization from where it just came from, so there's a refractory period, and we're going to talk about that. Okay? That was very good. All right, so let's do this. Resting membrane potential of a cell is due mainly to what? Resting membrane potential of the cell is due mainly to what? Open sodium channels. These are the only choices that you have. Open potassium channels. Saltatory conduction. We haven't covered that yet, but if you've read ahead, then you'll be familiar with it. Differences in calcium concentration across the membrane. How many say A? You got your clickers. A. B. How many say C? How many say D? The B's have it. Okay? It's faster than the clicker response even. You see that? So why? Open potassium channels. Why does that influence the membrane potential?
Because the potassium channels are always leaking.
They're always leaking, and they're leaking what? Positive out, right? So that means it leaves a negative inside. Okay? It would not be a fair question if I would have put sodium potassium ATPase, or if I would have put nucleic acids, mRNA, and DNA, or those choices would also be yes choices. Okay? But those weren't on here. This is a homework assignment. You're going to have 2. I want you to complete this table. And I actually want you to bring it with you to turn in. Okay? I'm going to repeat that. I want you to complete this table, and I want you to bring it with you to turn in. Huh? Is it in the book? Yeah, it's in the book. But you should be able to figure it out. I'm going to explain it and how you're going to do it, but I'm not going to tell you what the answers are. Here you've got the ion. Here you've got the intracellular concentration and the extracellular concentration. Those little brackets are chemistry notations that mean concentration. So you can see that inside potassium is high, outside it's low. You would agree with that, right? Sodium is low inside and it's high outside. And chloride ion follows sodium, so it's high outside and it's low inside. Now, we've got 2 forces that we're looking at. We have a diffusional force, which is the direction that it's going to go based upon its concentration. So it's a concentration-based force. And I want you to tell me, you're going to input here into or out of the cell. Is the diffusional force, given this data, into or out of the cell with respect to sodium? What about the electrical force? Is the electrical force, don't answer it out loud, you're doing it on your own, is it into or out of the cell for sodium? And then same thing, same 2 questions for, there's 4 questions for potassium. Is the diffusional force for potassium into or out of the cell? Is the electrical force into or out of the cell? Okay? You should be able to do it even just right now. And then we'll go over it on Tuesday. If you're confused, I want you to struggle with it a little bit and see if you can figure it out. Okay, but I will reveal the answers to you on Tuesday. We'll go over this in the SI or the Peer TA session this afternoon. So if you want to do it sooner, come. Okay? You're going to have another homework assignment, so don't put that sheet of paper away if you're going to do it on the same sheet. Maybe leave a little space. One option is just print out the slide. Write your name at the top. Okay? Or print out this slide and the next slide and put your name, at the top of that page. Okay, so let's go over the action potential that you covered on Tuesday. These action potentials, they occur in an area where there's a high concentration of voltage-regulated gates. This area is known as the axon hillock. This is kind of that funnel that you kind of saw from the video. And at that point, we refer to it as the trigger zone, that axon hillock. It's that funnel portion as it goes towards the axon from the soma. And as you move towards that funnel or that trigger zone, as it kind of tapers down, you have a higher density of voltage-regulated gates in that location. A local potential, we said earlier, can cause an action potential, and they start to summate at that funnel. And if they summate and they reach minus 55 millivolts, then it triggers an action potential. So in this picture, right, you went over the action potential, but here's threshold at minus 55. Remember, 0 is here, so numbers down here are further away from 0. Minus 70 is our resting membrane potential. These EPSPs, there's one, there's a second one, here's a third stair step, a fourth, a fifth. The fifth one gets you to the minus 55. That triggers the sodium gates to open. Let me repeat that. You're at minus 70. You have 5 summated, local, otherwise known as graded potentials that are excitatory postsynaptic potentials. The fifth one crosses minus 55. That triggers the action potential. Make sense? Okay. So let's look at this sequentially. Again, I know you went over on Tuesday, but I want to do it comprehensively. And you're going to go over it a third time next Tuesday. Okay, this is the real physiologic mechanics of what's going on. These are the mechanisms of nerve physiology. This is how we send electricity down a neuron. We say that we fire a nerve. What does that mean? You depolarize it to create an action potential. That was a beautiful answer, but anyone outside of this classroom would not understand that. That is totally correct. What does that mean when a nerve fires? Okay, you reduce the membrane potential, or I would say you make it closer to 0. How about just simply you send electricity down the nerve? That's how you explain it to mom or dad, right? Or unless they're like a nerve physiologist, okay? Or a doctor, or probably a nurse or a PT. But if they're in a different field and they're surprised that you're going to go work with patients, then they probably won't get it. So you're going to have to explain it to them. But what that means is you're sending electricity down a nerve or down a wire, just like what happens in the wiring of this room, or the wiring that's sitting around your neck as you put those earbuds in your ears. They have a casing on the outside that's insulated. Our nerves, our wiring has casing. We call it myelin, and we'll get there. So that insulates the signal. Why do you insulate the wires that are sitting around your neck? You don't shock everybody, okay? You don't dissipate and lose the signal. So it's for signal fidelity. A better insulated wire is more expensive. Did you know that? Any of you that have ever done anything with stereos? You have a real monster cables. Anybody heard of monster cables? So monster cables are these technologies that have really fat diameter, large gauge wire with really expensive insulation. And it can send high quality sound or audio, video, long distances. And they're really expensive to purchase. And it's not just because they're cool looking. It's actually because they really work. So the thicker the insulation, the higher the fidelity of the signal. That's not any different than our nerves. Okay? So we propagate the signal. We trigger an action potential by reaching threshold, and we send it downstream. So use these analogies like wiring and wire insulation to help you understand what the heck is happening. Because a lot of times students just struggle with, I just cannot picture what is going on when a nerve fires. Okay, but you flip the switch on the wall and the light goes on. That electricity went all the way from the switch all the way to the light and back. Well, you think to wave your hand or use the laser pointer. Electricity is firing from your cerebral cortex to your hands and back that quickly in order to make that happen. That's what happens. And there's not like little strings that are moving us, right? We have electrical impulses that are being transmitted or firing down the nerve. So the way that we move electricity or current is by moving ions that have a charge. So you shuttle a sodium that has a positive charge one direction. You shuttle a potassium that has a positive charge the other direction. You're just moving electricity that's attached to a molecule. Does that make sense? That's how it works. So if you can't put those pieces together, you're really going to struggle with the memorization part. You'll memorize, because I know a lot of you are really bright. But if you can understand the why and the how behind it, it should be a whole lot easier to do well in this next exam. So we're moving electricity. We're shuttling electricity as nerve impulses when we fire a nerve, because we're moving ions. We have to move those ions because that's where the electricity is attached. Because those ions have a charge. That's why the chemistry as a background is important. That's why we cover it in the Unit 1. Right? That's why we look at the periodic table. And you think about charged elements. It is relevant to physiologic systems. Okay? So, just for example, you've heard of these terrible situations, and sometimes they're contests of people that die from consuming too much water. Have you heard of this? This is true. Some of you are like, yeah, I heard about that, but I don't believe it. Trust me, it is totally true. And a lot of times it happens like in fraternity settings or in clubs where they're kind of challenging each other, and there's a lack of understanding that this could be really, really bad. So what happens if you dilute the ionic balance of your extracellular fluid to such a great extent that you don't have a separation of charge?
If you have, if the concentration outside the cell is too diluted and there's no concentration gradient, ions won't go in and out of the cell.
Right.
And then there's no...
Yeah, you're like, so big deal. You can't scratch your butt. Can't, scratch your, yeah, you can't contract your heart, dude. You can't breathe. So you'll die because you're not shuttling these impulses because you've diluted the ionic concentration. You've just turned off the electricity. Okay, so that's how it works. That's why these people can overdose on too much water. Okay, so we have sodium ions that arrive at the axon hillock. So that axon hillock, if you have a nerve, I need to have a drawing. If you have a nerve that's at the entry point to the axon. So if we look at the entry point to the axon, right, and we bring in from here, from these different areas, this is where signals can come in, right? These are our dendrites. And then right here at the nerve, as we draw it, this zone right here, where it necks down, this is the axon hillock. Okay? And you have a high density of voltage-regulated gates at that funnel. It looks like a funnel. And it's also synonymous with what we call the trigger zone, where it fires, right? Kind of makes sense. So we've got sodium ions arrive at the axon hillock. They depolarize the membrane in step number 1. That's right here. This is this rising phase from minus 70 to minus 55. And these are local potentials. In the previous picture, we saw that they summated, and we had the stair-stepping as they increase in their response. Once it reaches step 2 at threshold, typically this is minus 55, we trigger our fast sodium gates to open. Those fast sodium gates open and sodium rushes in, and that's why this is such a fast increase. It's not like a slow little slope that goes like this, right? That would be slow. It actually is really quick. Once it hits the trigger, it fires almost immediately. So the sodium fast gates open quickly, and then you have these slower voltage potassium gates that are opening. Well, they open very slowly, so their response is masked by the response of the sodium fast gates. You get to step number 4 here. As it passes 0, the sodium channels begin to close here, as it passes 0. By the time you get to the top of 4, they're completely inactive, and then they close. And so they close quickly, and that's why it goes sharply down. If they close slowly, it would actually have more of a sloped top to it. And then with step number 5, same picture, but just different numerical descriptions. Step number 5, sodium gates are closed and they're inactive. Right? They started closing over here at about where it crosses 0. They were totally closed at 4. So they're still closed here. So sodium gates are inactive and at this point closed. Slow potassium gates are fully open, and potassium is flowing out of the membrane. As you flow potassium out of the membrane, you take a positive charge out. That brings the inside back negative. You with me? So you repolarize on this side, and you turn off or you close those slow gates slowly. And that's why it's not a sharp shut at the bottom. It's kind of this really slow slope, because these slow potassium gates close slowly. And then what ends up happening is more potassium leaves the cell than the amount of sodium that came in. And so you have this hyperpolarization like we just talked about. So that's an overshoot. It's a little bit more negative than it should be, but that's really important because that prevents the signal from going backwards. And I'll show you that. I have another picture of how that works. But that overshoot is hyperpolarization, too much polarization. The student might ask, well, why do we do that? It seems inefficient. Well, it's inefficient for a cause, because the inefficiency has built into it the fact that you won't send the signal in the wrong direction, because that would be more inefficient. And then slowly over time, the sodium-potassium ATPase pump helps to reestablish the correct balance of ions inside and out, and you return it back to resting membrane potential. Okay? So this is the mechanism. These two slides are really the meat of the material. And if you can explain what's going on in these slides every step of the way, then you have a pretty good handle on neurophysiology. And what's important is that muscle physiology utilizes all of these concepts. And that's the next unit. And that is historically the next hardest exam. Yeah, I mean, I'm doing this a while, so I can tell you exactly how they line up. You know, I can predict what the average test scores are going to be for these next two exams. Yeah. What's that? Which are? They're going to be probably, typically, in the upper 60s. Yeah. The average of the last one was 73. There was a question in the back. Yes, absolutely. Question one is hyperpolarization the cause of the refractory period? Very much so. That is what causes it.
If the average of the exam is like in the high 60s, then maybe that should tell you something.
It does. I just told it to you. It's really tough material. Yes.
So after this, so free sodium leave the cell.
Right.
Potassium still in, right? The cell.
Come into the cell. Yes. That's the sodium-potassium ATPase pump. Pumps 3 sodiums out and 2 potassiums in, and it uses an ATP to do that. Right? So you know that's why you really need the ATP energy. Okay. So this action potential, in contrast to local potentials, this is an all or none response. And I wasn't trying to blow you off with your question. That's why I'm sharing it with you. It is tough material. We do bonus opportunities. You have homework assignments. You have quizzes. These are all points that help bring up those averages if you do that work. If you don't do that work, then all you have are the exam scores. But that's why I put those points into the class. Because you're right, it does tell me something. And I do care about it. That's why I'm telling you ahead of time. Okay? So don't take it lightly. It's tough material. If you're getting it, wonderful. The beauty of this arrangement is you've got 4 different places you can get this information from. You had Aaron on Tuesday. You've got me today. You have Jody as an SI, and you have Jordan as a peer TA this afternoon. So if I'm not explaining it to you well enough, or in terms it's connecting with you, you can reach out to 3 other sources to get help. Right? And that's a great thing. If it's working for you with me and you want to come to my office hours, fantastic. But I know that the way I lecture may not resonate with every single style of learning. So ask more questions. Okay, that's why we have these extra sessions. Okay, all or none response, the action potential. It is non-decremental. It does not dissipate. So once you get to step 2, you cannot turn back. This is the point of no return, if you want to write it down. So it is all or nothing. It does not go away. It fires after it's decided to reach threshold. It's irreversible. You can't stop it. Now, the refractory period that was appropriately brought up in the back and in the front of the room is shown here. So, after we fire an action potential, we have an absolute period that's shown in orange. Once we get to the hyperpolarization, we have a relative refractory period. So the absolute refractory period is an area where you cannot fire another action potential because you don't want to ruin the signal. You don't want to fire an action potential, send another signal on top of it, and confuse the body of which signal is which. So in an absolute, it's absolute. You cannot fire another action potential at that same time. Relative refractory period. Well, this one is refractory. The whole point of it is to prevent the signal from going the wrong direction from where it came. You want to propagate it forward, but you could trigger a new action potential if you had a very strong stimulus. So you can overcome that with a strong stimulus if it was really critical to use that same neuron at that time. So why promote propagation of the action potential forward with using the refractory period? Well, it's intrinsic into the system because you bring in a little too much potassium using a slow pump that closes slowly, so too much comes in. So sometimes students think it's slow. How is it bringing too much? It's slow to open and it's slow to close. So it just closes slowly so more potassium can get in. Does that make sense? And so you hyperpolarize it, and that's already your intrinsic mechanism, built in to the design to allow for a refractory period. It's kind of cool. Here's your second homework assignment. I want you to compare and contrast. I told you, you're going to have to know this. Compare and contrast action potential to a local or a graded potential. So, for example, the characteristic here, you're going to answer yes or no. So, is it an all or none event? Yes or no. For action potential, yes or no. For graded potential. Is it decremental over time space? Yes or no. Yes or no. Don't shout it out. Test yourself. See how well you can do. See what you could do on your own without looking it up. Just try it. Then go look it up. Make sure you got the right answers. Okay? But it'll help guide you on how well am I getting this stuff. That's the whole point. These are good tools if you choose to use them. There's a question? Thought I saw a hand. Okay. All right, let's look at some other propagation factors. If we look at the action potentials and how they travel, this diagram might do a better job of explaining why the refractory period keeps it from going backwards and propagates it forward. So here's a much better drawing than my chicken scratching. Here's our cell body. Here's our dendrites. These dendrites bring it into the cell body, and here is that axon hillock right here. You see that little funnel? That little taper down is this region right here is the axon hillock. They stop shaking. Okay. Here is our axon. So at the level of the action potential has already been fired. This box is what we're blowing up on these three pictures. So let's look at what's going on in that box. The first one, you can see green inside the cell, slightly negative. Green means go. That's an excitable membrane. So it's excitable here, and it's excitable back here. Red, this is where the action potential is taking place, and that's your absolute refractory period. Right? See how it's positive inside the cell? That's where the actual action potential is happening, right there in red. Right behind it is where it came from, and right behind it is a relative refractory period because the membrane is more negative than normal. So electricity likes to travel in the pathway of least resistance. Right? So if any of you hike Humphreys, it's at 12633. Okay? It's the highest point in Arizona. And you get to above the timberline. So there's a point where I am the tallest thing up there. It's a pretty awesome feeling. Okay? And if it's stormy and there's electric... Yeah, that was a short joke, but it was at me, so that's okay. That was a little too much. Let's back off the stat on it, but I appreciate the laugh. Electricity likes to find the pathway of least resistance, so that's why electricity strikes the highest object, because that's the least resistance pathway. It doesn't have as far to go. So here, which direction is it going to stimulate the membrane to travel? This way versus this way. And this is minus 70, this is like minus 85 or 80. So this is easier to stimulate, so that's why it moves like a flip book in the rightward direction. Okay? Now, if you have a bare axon, you would travel in this mode. We call this continuous conduction. Continuous conduction is shown here in an axon that is not covered. That's like a bare wire. An unmyelinated axon. Well, we have these axons that are myelinated. Somebody mentioned nodes of Ranvier, or Ranvier, if you're an American. And Ranvier, right? Because that's not America, that's its own place. Okay. Just kidding. Nodes of Ranvier are these bare spots on a myelinated axon. A myelinated axon travels via a different mechanism that's what's shown here. It's called saltatory conduction. And it hops, the signal hops inside the cell from one node to another. And I will show you how that looks. So, what does myelin do? Well, it influences the speed of conduction. There's two main things that influence the speed of conduction. The slide is blank, but you're supposed to write them down. Number one, diameter. The diameter of the axon. The larger the diameter, the faster the transduction. So, the larger the wire, the larger the gauge of the wire, like a speaker wire, the faster the conduction of the signal. The smaller the diameter of the wire, the slower, and the cheaper the wire. Okay? So diameter, number one. Size does matter. Bigger, faster. Think of trying to drink a milkshake through a straw. If you have a large diameter straw, you can get more milkshake per unit time. If you have a small diameter straw, like a little red coffee straw, you're going to blow aneurysms in your head trying to get the milkshake. Okay, number two is myelin. Myelination is the second thing that influences the speed of conduction. So look at this graph. Myelin reduces the resistance, and we've got two things plotted here. We've got conduction velocity on the y, and we have fiber diameter on the x. And you can see that the larger diameter the wire, or the fiber, excuse me, the faster the speed of conduction. So if it's a 20 micron fiber, it's faster in conduction than if it's a 5 or a 2.5 micron. But look at the influence of myelination. So myelination, the myelinated fibers exaggerate this diameter relationship. So myelinated and larger diameter is the fastest signal that we could have. But to myelinate a fiber is expensive biologically. It takes a lot of energy to wrap myelin around a fiber. Okay, so you only use it where you really need it. Oh, let's see if my link, shoot. Let's see if my link works. No whammies, no whammies. Good. Okay, so here is an unmyelinated axon, and the signal is moving ever so slowly. Here it comes, there it is. And you can see on a saltatory conduction of a myelinated fiber, this signal hops from one node to another. The signal actually hops inside the axon. It travels inside the axon. I'll kind of explain that here in a moment. But this is the difference visually of what we're seeing. Now, if I go back, oops.
What you will see and hear in this presentation is the development of myelin in the peripheral nervous system and the propagation of the action potential along a myelinated axon. This multimedia presentation will be most helpful if you already have a good understanding of the Schwann cell and the electrochemical process of the neuron, called the action potential. The Schwann cell forms a protective covering around the axon. Schwann cells start to develop in the embryo and continue to increase the wrapping around the axon through childhood. This development increases the thickness of the wrappings, which peaks in adolescence.
See how it's wrapping it?
This is why teenagers have such quick responses. The Schwann cell contains the typical cell organelles and cell membrane structure. However, notice as the Schwann cell surrounds the axon that the nucleus and other organelles are squeezed to the outside wrapping of the cell. This outer wrapping of the Schwann cell is called the neurolemma. The inner lining is made up of layers upon layers of cell membrane. This inner wrapping is called the myelin sheath. You will recall that the cell membrane, called the fluid mosaic model, is made up of a bilayer of lipids integrated with proteins. The thicker the myelin, in other words, the more layers of cell membrane making up the myelin, the more advantageous it is to the axon. One advantage is the regeneration of severed axons. Another advantage is an increase in the speed of the propagation of the action potential along the axon. The rest of this presentation will concentrate on the increased speed of action potentials down the length of the myelinated axon. Here is the neuron.
Okay. So I'm going to show it to you because she's starting to put me to sleep. So if you remember, that phospholipid bilayer has proteins embedded in it. So developmentally, it's like taking a roll of tape around a pencil and wrapping a layer after layer after layer. Does that make sense? So that's what you were seeing visually in embryonic development. So our myelinated fibers have a cell, a Schwann cell, that wraps around the axon, and as it wraps around the axon, it's leaving a tail of phospholipid bilayer behind. And that tail is a fatty, a phospholipid, with protein embedded in it. So it's like a fat, proteinish layer. That insulates that region. And then there's another one that does it a little distance away, and then another one does it a little distance away. So you have these bare spots, because it would be really expensive to have all of the axons all the way down the length being wrapped. We can't afford that much biologic energy. So we wrap a certain segment of them, maybe approximately a third to a half of the actual distance is wrapped and covered in myelin. So if you look at this drawing, so here is the myelin. If the myelin is there, it's insulating and covering it. Can you transmit any ions across that fatty covering? No. So you only move ions at the bare spots, at the nodes of Ranvier. Okay? That's where the sodium channel opens and sodium comes in. That's what you're seeing right here is the sodium channels open here and the sodium floods in, and then potassium floods out, and then the signal travels underneath the myelin sheath and pops out in this spot. And as it travels underneath the sheath, you don't have to move any ions, so it travels much faster. Make sense? There's no exchange that needs to take place. It exchanges here, travels here, exchanges here, travels here, and it does this hopping motion inside the cell. You with me? So you can kind of see similar types of diagrams we saw before. Green is excitable, red is where the action potential is, and yellow is the refractory period. And it moves forward just like we saw before in unmyelinated continuous conduction. So continuous conduction are bare axons, unmyelinated. Saltatory conduction is a faster conduction velocity or speed that's performed at the nodes of Ranvier where the sodium channels are inserted and can actually move. So clinically, why do we care? Well, there's actually a disease known as multiple sclerosis that is a demyelination of the nerves. And it's an autoimmune disease. And what happens is the body attacks the myelin and breaks it down and destroys it. And it's a disease that is perpetuated over time because more of the myelin is lost a little bit every year. So somebody that's been suffering from MS for a year typically doesn't have as many symptoms as somebody that's been suffering from MS for 10 years or 20 or 30. So you can see that blindness will eventually happen. You can see that there's problems controlling muscles. There'll be problems with walking later in life as the disease progresses. The immune system specifically is attacking the myelin sheath. In this picture, this cartoon diagram in the middle, this actually is out of a Nature publication, and these are the images of immunofluorescent chemistries. So here's sort of a normal soma. These little channels are the sodium channels. See these little channels right here? Here's the myelin. Here's the channels at the node. Here's the myelin. Here's the channels at the node. This is the immunohistochemistry of a normal myelinated axon. You can even appreciate the white color in this diagram of the myelin sheath. And then the red marking here, that's your sodium channel. And the sodium channel is usually bound by these Caspers, which are the green. And so you know specifically if there's a red bound by two greens, that is a functional sodium channel. Okay? This is what it's normally supposed to look like. Well, as you progress in the disease of demyelination, what your body does is there's a compensatory mechanism for patients with MS to upregulate the production of sodium channels and insert them into the regions where the myelin is lost. You can see myelin's lost here. Body compensates by inserting more sodium channels. But eventually it can't keep up and the nerve is lost. So if you look at the immunohistochemistry on the right, look at the amount of red that's been inserted in this condition here to try to compensate for the lost myelin. So the speed of conduction velocity in our multiple sclerosis patients, our MS patients, is slow. And there's a period of time where they're kind of stable because the body compensates, but then once you lose the nerve and you don't have the ability to insert any more sodium channels, you lose the nerve. Okay, so paper out of Nature in 2006, there was a pretty pivotal paper that kind of showed why this is such a problem. Axon diameter, we kind of talked about that. Larger is a faster transduction. The larger the diameter, the faster the speed of transmission. So resistance to current with flow is less in a larger diameter fiber. That's why it works so well. Neurotransmitters is where we're going to pick up on Tuesday with this slide. We're going to talk about neurotransmitters and the two different types, and then we'll move into lecture number 3.